So there were two parts, really, of modeling with exponential functions from 4.6. That I did not get to yesterday. Well, I think I started the first one with you. But I didn't have it set out very well, so. The first, which I started, was radioactive decay. And radioactive decay is where the rate of decay, or the rate of deterioration of an object, is proportional to the amount of the material. And we talked yesterday about how taking 10% over 5 days doesn't mean you've taken 50% off. Because each time you take 10% off, there's a little bit less to take 10% of. Okay. That this rate of decay is generally given as a percent. And that the most common, well, not common necessarily, but the most familiar, we'll just say common, is 50%. And that this is known as a half-life. And it measures the amount of time it takes to have half left. So a radioactive substance with a mass or amount of m sub 0 and a half-life h the amount remaining at time t is modeled by the function m of t, or the amount at time t, is equal to m sub 0 to the negative t over h. Where m sub 0 is the initial amount, t is time, and h is the half-life. So the time to half. This particular formula is specific to when you know the half-life. If you have the relative rate of decay, then it's m of t is equal to m of 0 e to the negative rt. where m sub 0 is again your initial amount. T is your time. And R is the relative rate. Yep, I'll just do this. So these, I think I gave you or got these two formulas out yesterday. The part I didn't get out was the translation. Some of the time, or some of these problems or questions, give the relative rate and ask to find the half-life. So what I wanted to show you here is how do we convert the relative rate of decay in order to solve it for the half-life. For example, maybe we know that over a 3-day period, 10% of the viruses have decayed, right? So if we know that over a 3-day period, 10% have decayed, how many days will it take us to get to 50%? And it's just because people understand halves better than they do 10%, right? So if we start with 100 and I say what's half, you can very quickly get to 50. And then if I say what's half of 50, you can very quickly get to 25. People get halves better, which is the main reason we say half-lives. Not for anything else, really. All right, so if we start with the relative, which is the m of t, or the mass at time t, is equal to the original mass times e to the negative RT. Now, we want there to be half, right? So we want m0 divided by 2, or half of the original amount. And instead of t, we want the time to be h for the half-life. If I simplify this a little bit by dividing both sides by m sub 0, or the initial amount, I'm just going to get 1/2 equal to e to the negative RH. Now, because I have an e here, I'm going to take the natural log of both sides, using my law of logs to simplify this. Using the law of logs here will give me ln1 minus ln2. And if I use the natural log on the right side, that negative RH can come down front, and then I'll have the natural log of e, which should just be a 1. Now, there's another piece here. Do you remember what ln1 is going to be? Yeah, the natural log of 1 is just a 0. The log of 1 in general is 0. So I'll have a negative ln2 over a negative h is equal to r. Oops. Oh, yeah. Or if I needed to find, so I actually have two little mini formulas. If I needed to find the relative rate, I could use ln2 over h. And if I need to find the half-life, I can find ln2 over r. So this one is what I would use to find the half-life. But if I had the half-life and I needed the relative rate, I could use ln2 over h. That's kind of slick. Questions? All good. All right. Correct. Yep. You'll need these for some of the problems that are in the assignment. If they give you the half-life and they ask you for the relative rate, and some of them will give you the relative rate and ask you for the half-life. So you're just switching them back and forth. And sometimes it's like, that's exactly what they're asking you. And sometimes it's a part of the problem and you have to recognize that you need to switch, right? Okay. All right, let's try an example. Here we have a radioactive substance, polonium-210. It has a half-life of 140 days. You have 300 milligrams. Okay, so we are going to write a function, that's an FCN, to model the relative rate of decay. Then we're going to find the mass. So the remaining mass after 1 year. And then for part C, we want to determine when there will be $100 milligrams left. Okay. All right. So write a function to model the relative rate of decay. Relative rate of decay is m of t is equal to our initial amount, that's 300, times e to the negative rt. Did they give us the relative rate? Instead, they gave us the half-life. So we're going to need to use the conversion, which is that the relative rate is going to equal ln2 over h. So here's the thing. What's our h? Our half-life is the 140. So if you do ln2 divided by 140, you are not going to get a pretty number, right? It's not going to work out very well. So when those numbers don't work out, I tend just to rewrite them, and I'll use all of this as my exponent. This is fine the way it's written. I have also seen it just cleaned up a bit. Like that. Yep, because it's a negative RT. So it would be a negative T ln2 over 140. And that would be our M of T. So that would be our mass given time. And I would just leave it like this, because ln2 divided by 140 is some crazy decimal. And there's no way that I can guarantee that somebody else will round that to the appropriate decimal place, right? Unless I say. I will say a piece of advice from me to you, that if you come into a situation where you get a crazy decimal and you feel like you have to round someplace, keep at least 5 decimal places. Otherwise, your precision might be off when you put in your answer. Like you might have rounded too soon. So I would say keep 5 or 6 decimal places if you end up having to do it. Okay. So now we've got the second part, find the remaining mass after 1 year. We need to be careful because this says 1 year, but notice in our original problem, we were given 140 days. Right? So we were given our half-life in terms of days, which means I should convert 1 year is how many days. So I should use 365 because I should not use a year for t in one place and days for t in the other. They have to be the same unit, just like everything we did yesterday. Time had to be the same unit. So when I do this one, I'm going to do m of 365 is equal to 300 e to the negative 365 ln2 over 140. Oh, bless us. All of this is my exponent. Now, my recommendation is you type it into your calculator this way, just being careful. So I'll do 300 second e negative 365 ln2 divided by 140. And I get about 49.2 milligrams. Question. Okay. Part C says to determine when there will be 100 milligrams left. When they give me this 100 milligrams, they're giving me my mass at time t. I am finding t. So I'm going to have 100 is equal to 300e to the negative 365 ln 2 over 140. In order to solve, whoops, this should be a t, my bad. It should be a t. Yeah, tx, I'm finding the time, sorry. T ln 2 over 140. Now remember, our goal is to bring this down so it's no longer in the exponent. So I need to get this e to the exponent isolated. So I'm going to divide both sides by 300. And that's going to give me a 1/3 is equal to e to the negative t ln 2 over 140, taking the natural log of both sides. And as we've said before, ln 1 is just a fancy way to write 0. Now, to get the t alone, what do we need to do? Yeah, I'm actually going to go a little bit further. And I'm going to multiply both sides by 140 and divide both sides by ln 2, right? Essentially multiplying by the reciprocal. And while I'm at it, I'm going to put a negative on there. So a negative times a negative is a positive. So I've got a negative 140 ln 2. Negative times a negative is a positive. And I'm going to have a 140 ln 3 over an ln 2 is equal to t. This as an answer is not concrete enough. I need to know the time, right? This does not really tell me much about time. So I am going to need the calculator. 140 ln 3 divided by ln 2 is approximately 222 days. Does this make sense? Well, we started with 300 grams, right? Milligrams. And how long does it take to get to half? So at 140 days, we would be at 150 milligrams. So we would need more than that, more days than that, to get down to 100 milligrams. Okay? Questions about this particular problem? Okay, awesome sauce. Okay, our last application is one that has proven itself to be a lot of fun in terms past. People have been very excited for this particular sample and application. This is Newton's law of cooling. Now, there are several different ways to write this law. If you Google it, You could go down a wormhole you don't want to go down with a lot more difficult notation and explanation than this, okay? We are using it in terms of exponential decay, but some of the ways I've seen this written, because I know some of you are Googlers, you don't want to go to. Newton's law of cooling says this: the temperature of an object at time t is equal to the temperature of its surroundings. So if I'm in a room that's 72 degrees, T of S is 72. If I'm outside on my back deck and it's 94 degrees, then T of S is 94. So whatever the temperature is of the surroundings, added to D sub 0, where D sub 0 is the difference between the surroundings and the object, times e to the negative kt. K is known as a constant. It's a positive constant. It's a known rate and is different for each object. So for example, the degree of cooling for an ice cube, the rate of cooling for an ice cube, its K value, is different than the rate of cooling for a human body. Okay? So again, T of T is the temperature at time T. That time could be in days, minutes, hours, weeks, can be any sort of interval. T sub S is the temperature of the surroundings. D sub 0, whoops, is the initial difference between the object and the surroundings. K is a positive constant. And it is different depending on object. For the most part, K is going to be given to you, but there are a couple of problems towards the end of the assignment where you have to determine K. It's not particularly difficult, although some of them can be challenging. So my goal for the remaining 20-ish, 25 minutes is to go through a basic example and then one where we have to find K. All right, so let's do our first example. I'm going to call this a forensic file. This is why people like it, forensic files. The fact that we use Newton's law of cooling in forensics to determine the time of death or approximate time of death when it's unknown is the reason that many students through the last few terms have liked this particular problem. As morbid as it may be, it's also a little bit fascinating. Okay, so without giving you the entire case study, I'm going to provide you with some basic information. The normal body temperature in Fahrenheit, Garrett, is 98.6 degrees. This is not true for everybody. Mine's 97.7. I know that through trial and error, but it is generally accepted to be 98.6 degrees Fahrenheit. Okay. K value in humans, or the rate at which the body cools, is 0.1947. Now, to be perfectly honest, I don't know if that's actually true or if the book made up that number, but we're going with it because that's the problem. Suppose the room temperature is 68 degrees. Oh, sorry, not 68, 60 degrees. And T is in hours. All right, part A says to model this information using Newton's law of cooling. Okay. As a reminder, Newton's law of cooling says the temperature at time t is equal to the temperature of the surroundings plus the initial difference times e to a negative kt. All right. T, the temperature at time t is equal to T of S, or T sub S, is the temperature of the surroundings. The temperature of the surroundings are
60 degrees.
Yep, 60 degrees. Plus D sub 0 is the initial difference between the object, that would be the body, and the surrounding. So that would be our 98.6 minus the 60. Times e to the negative k times t. There we go. This is going to give me the temperature at time t. T is in hours. Okay. That's all I had to do. Just plug the numbers into the appropriate parts, figure out what the difference was, put it all back together to model the function. So if the body temperature measures 78 degrees Fahrenheit at 10 a.m., how long have they been dead? See, that's the morbid bit right there. Okay. So what you need to figure out is, what is this 78 degrees? Where does that go? And what are we trying to find? We are finding time, right? So that 78 degrees has to be, I mean, I've got that, I've got that, I've got that, I'm finding that. So 78 degrees Fahrenheit has to be the temperature at an unknown time. Alrighty, and now I need to solve this for t, much like I've been doing throughout the last couple of sections. So I'm going to subtract 60 from both sides. I'm going to zoom in on this now. Okay, I'm going to divide both sides by 38.6. Now, you'll notice again, I did not work out what that number is. Because if I do 18 divided by 38.6, I'm not getting a nice number. I'm getting a crazy decimal. So I made a decision, personal decision for myself, to leave it as 18 over 38.6, because I can use my law of logs to rewrite that as ln 18 minus ln 38.6. And then when I take the natural log of this side, the e will cancel, and this negative 0.1947t will come down. And what that means is that when I type this into my calculator, I'll get a more exact answer than trying to type in the natural log of all of this junk. Right? I don't have to save that long decimal. Now, you may come up with a different way for yourself to get all of those, and that's fine. Maybe you know how to use your store function on your calculator and you're fine doing that. That's great. So now I'm going to type in what I've got here, ln 18 minus ln 38.6. I'm going to hit enter. And then I'm going to divide that by my denominator, negative 0.1946. And I get a 3.918. And this would be in hours. So they've been dead not quite 4 hours, which means if they were 78 degrees at 10 a.m., they've been dead since about 6 a.m. Let's see if I can get closer. Minus 3 times 60 is 55. They died at approximately 6:05 a.m. Yep. Okay. Questions about that problem? Okay, excellent. Okay, I am going to get away from the morbid one now. We're going to do one that's a little bit more mundane. If anybody's ever worked in food service, this is problem number 27 from your textbook. It's cooling a turkey. What's the danger zone? Mm-hmm. I don't remember exactly myself, but I know it's like between 120 and 160, I think, or 165 maybe. I don't know. They've probably changed it in the 20 years since I've worked in a restaurant. Um, okay, yeah. For whatever reason, in my head, I'm stuck at 140. Like you don't let things get to 140. So that may be what it was 20, 30 years ago before we knew better. Okay. All right. So we're going to talk about it this way. Let's say a turkey is taken out of the oven at 185 degrees Fahrenheit and left in a 75-degree Fahrenheit room. Okay. If the temperature of the turkey is 170 degrees Fahrenheit after 10 minutes, no, let's do 15. Find K. All right. Part B, and I think I probably switched the numbers up a little bit. What is the temperature of the turkey after 30 minutes? And we could ask that a little bit differently. We could say, is it in the danger zone after 30 minutes? Has the turkey gone, we wouldn't say bad, but, is the turkey usable, edible, whatever, after 30 minutes? So, okay. Let's take a look. Looking at part A. The turkey is cooling in a room. This is Newton's law of cooling. T of T, temperature times T, is equal to the temperature of the surrounding room plus the initial difference times e to the negative kt. You have several pieces of information here. What is the temperature of the surrounding room?
75 degrees.
This is 75. What's the difference between the initial temperature and the surrounding room? No, the initial temperature of the turkey and the surrounding room. You're close. That's going to be the 110. Yep, because we want the initial temperature as it was given to us and the surrounding room. E to the negative k, which I'm finding k, that's what part A is. And how much time has passed? And when 15 minutes have passed, then T of 15, or the temperature at 15 minutes, is now I just need to solve this for K, much as we solved it for T previously. So I'm going to have 95 is 110 e to the negative k times 15, or 95 over 110 is e to the negative k times 15. I'm going to take the natural log of both sides, and I'm just going to use, guys, this reduces. You could reduce this to 19 and 22 if you wanted, and you should get the same answer, but I'm just going to use my law of logs. ln 95 minus ln 110 is equal to a negative 15k. That would go out front, ln of e. ln 95 minus ln 110 divided by a negative 15. Right? I got a long decimal. Now, this is a situation where you get a value of k, and it's a very long decimal, and I would keep at least 5, if not 6 decimal places. So I would keep at least 0.009774. And sometimes that won't be enough. So if you're working on a problem and you think you need to keep 5 or 6 decimal places and you're still getting it wrong, feel free to send me a message saying, what's happening with this one, Amy? Because I think I'm keeping enough. If they're not, sorry. Yep. Okay. Then part B says, what is the temp of this turkey after 30 minutes? So now they want you to use this K value in the next problem. So T of 30 is going to equal, same problem otherwise, 75 plus 110 e to the negative 0.009774 times 30. So the second part is just putting in the number you got. And I'm getting 157.04. So after 30 minutes, we are in the danger zone. Questions on that guy? Okay. Garrett, sometimes I feel like it's your nap time. All right. No, now it's 4 o'clock. It's definitely nap time now. So, all right, just as a recap. So then I'm going to change the due date on this assignment till Monday. Monday, I'll take any last minute questions on it or anything else from chapter 4. Tuesday, I'm also open for questions from chapter 4. Tuesday, your chapter 4 test will open at 8 a.m. and it's due by 11:59 on Thursday. All right. Okay, if you guys need anything over the weekend, please don't hesitate to send me a message or shoot me an email. Either one.